Again, welcome to DSRT 734 class. This lecture covers types of random variables. In quantitative random variables, we have discrete random variable, which is based on counting, and also continuous random variables, which is based on measurement. So example of a discrete random variable can be how many patients visit an hospital. We have 20 patients. So normally it's going to be a whole number, 20, 25, etc. Now, continuous random variable example can be what is the weight of a patient? 150.7 kilogram. So again, it can be a decimal value. But a discrete random variables will always be a whole number because it's based on counting. So here we see a discrete random variable. It's a random variable which has a countable number of possible outcomes. When describing a discrete random variable, we should do the following. State the variable, list all of the possible values of the variable. Then we determine the probability of these values. So let's say, for example, we are going to, again, toss a coin. So I will state my variable, tossing a coin. Now list all of the possible values of the variable. If I toss a coin, I have only head or tail. Now, next, determine the probability of these values. Since we have only two, head or tail, the probability of each one will be 0.5 or half. We know the first rule of probability, we say the total values of a probability is 1. So let's see an example here, random phenomena. We should toss a die and observe the outcome of the toss. So first, we need to identify the random variable. Here we say the outcome of the toss of a die. Let's say it's X. Now the next, what is the range of the values? Since a die have a 6 side, it will be integer values between 1 to 6. Inclusive means including the 1 and also the 6. So from 1 to 6. Now, what will be the probability distribution? So since the outcome of the toss of a die and the probabilities are given below, the probabilities are deduced using the classical method and assumption of a fair die. If it's a fair die, that means each of the 6 sides have the same chance of getting it. So this means it will be 1/6 each. Now the total of 1/6 up to 6 will give us 1. Now we have another example. The number of defective integrated circuits received in a batch of 1,000. Now, each outcome of the random variable is a numerical measure whose range of values is given below. First, they say we should identify the random variable. Here to be what? The number of defect integrated circuits in a batch of 1,000. That is the phenomena. The number of defective integrated circuits received in a batch of 1,000. Now, the range of values, it will be between 0 and 1,000 inclusive, which means 0 means there's no defective, maximum is 1,000. Then what will be the probability distribution? This can be unknown because we don't have a fair chance. Now, another example here, we say the head nurse of the pediatric division of the Sisters of Mercy Hospital is trying to determine the capacity requirement for the nursery. Now, she realized that the number of babies born at the hospital each day is a random variable. She will have to develop a description of the randomness in order to develop a plan. So first, we need to identify the random variable. In this case, it will be the number of babies born at Sisters of Mercy Hospital each day, based on the phenomena. Then secondly, the range of values, it can be integer from 0 to some large positive number. Then probability distribution is unknown, but could be estimated using the relative frequency idea that we went through in section 6.1. That is chapter 6 of the course textbook. Next, we talk about continuous random variable. Now, continuous random variable, as we said, is based on measurements. So this is a random variable that can assume any value on a continuous segment of a real number line. It can be a decimal number, a whole number. So we should know that for a continuous random variable, we specify the probabilities with probability density functions. So let's see an example. Here we have a local restaurant has an express policy that states that each lunch will be served within 15 minutes of ordering, or it will be free. Obviously, the restaurant is keenly interested in not give away its product and in delivering on its promise of a timely lunch. But the length of time to prepare each meal varies because of the differences in preparation time for each dish. Now, the load on the kitchen and the experience of the chef and the waitresses. So again, the length of time, in this case, the local restaurants want to spend not more than 15 minutes to order for food, to get ready the dish. Now, if it's over 15 minutes, you have to give out the meal for free. But the length of time also to prepare each meal will vary because there's differences in the preparation times of each dish, and also the load on the kitchen, and also the experience of the chefs. And the more experienced, maybe the faster they will be, and the waitresses. So we should identify the random variable here to be the time between the ordering meal and receiving it. Now, the range of values can be from 0 to infinity. We don't know. But we should know that S is measured on continuous scale. Then probability density also should not be known, but could be approximated using historical data. So that will be the conclusion of these lectures. Again, these are very short lectures. Our goal here is to give the definition, the difference between, again, a discrete and a continuous random variable. Thank you.